So far, what we've looked at is all monosaccharides, so single rings and single straight lines of sugars. Now we're going to shift gears and get just slightly more complicated and look at disaccharides. So a disaccharide is going to be made up of two monosaccharides, and we'll see a acetal is what links them, and the acetal is going to be an OCO arrangement of atoms. That's in contrast or very similar to a hemiacetal, which was OCOH. And this acetal, another term for it is a glycosidic bond, or sometimes you'll see glycosidic linkage. All right, oh, sorry, we're off the top there. So we're gonna see acetals that link two monosaccharides together, and an acetal and a glycosidic bond are used interchangeably. Okay, this is more a chemist's name, and this is more a biochemist or biologist name. So with the disaccharides, we want to come to the molecules that we see below here, and we want to go looking for these hemiacetals and acetals. So that would be a first good thing to do. So if you take a look at this molecule, this is maltose. Maltose is two glucose molecules, so it's identical rings. And if I look at this, I look at these O's in the ring, and that's going to be a good hint for where there's a functional group. So here's an OCOH, so that is a hemiacetal. And then right here, O in the ring, again, links to another, so OCO. So that is going to be an acetal, or a glycosidic bond. So I can find those functional groups to start with. Then if you can remember, in the middle of each of these would be my anomeric carbon. So I highlighted that a bit in pink there. This link right here is called my glycosidic linkage or glycosidic bond. And with that linkage, I want to be able to describe it in terms of what's its orientation and where in the rings is it connected to. So we're going to use numbering like we used numbering when we did our naming and things before. Our anomeric carbon, we're going to label as carbon number 1. Remember, we give low numbers to carbons that are near functional groups. So this carbon's actually right in the middle of a functional group, so we're going to call it carbon number 1. And then we're going to count away from that oxygen. So this carbon would be carbon number 2. This carbon is carbon 3, 4, 5. And normally we would have stopped in the ring, but with sugars we go up here, and this final carbon we call carbon number 6. So we number all the way around. Similarly, on this ring, I go to that anomeric carbon, and it's going to be carbon number 1, and I count my way around 2, 3, 4, 5, and 6 outside of the ring. And so then when I go to describe this linkage, I'm going to describe it as a link from this carbon 1 to carbon 4 in the other ring. And the final thing I want to describe is what's the orientation of this bond going down. And so this is where I want to come back to my anomers that I looked at before. If the orientation is angled down, it's an alpha linkage. And if the orientation at that acetal is going up, for the O, it's going to be a beta linkage. So down is alpha, up is beta. So if I can come back here and look at what's happening, I can see that it's pretty clearly going down, right? And so I call this an alpha 1 to 4 linkage that's holding these two glucose molecules together. So you need to be able to assign those numbers, figure out the orientation, and write something that looks like this. You'll see some variation in how they're written, sometimes with parentheses or not, but this alpha is telling me the position of that first carbon, and then the 4 is what it's connected to. There are more complex sugars than the few that we'll see, but you're going to see the ones we label are all fairly simple and straightforward. So that is our, and I'll just highlight this pink here to say that was the orientation of that anomeric carbon. So that is kind of looking at our disaccharides. The next thing that we want to do with our disaccharides is hydrolyze them. So plus water, and then we would have an enzyme that was specific to our sugar, like maltase, all right? So we're going to see a hydrolysis reaction here. And if you can remember, hydrolysis was water used to lyse or water used to break it. This acetal group is going to be like our esters and like our amides were, where that's what gets chopped, okay? So When I chop it, I'm going to end up with my two separate rings. Just copying carefully here, okay? And then I'm gonna work from this linkage first. So this was angled down, and this was angled down over here. So this is what I'm going to break here, okay? I'm adding a water, which means I get to add an H and an OH. And so where the bond was broken here, I'm going to add an H to one side and an OH to the other. So that, just like in the other hydrolysis reactions, I end up kind of replacing that bond that was broken. And then I just want to copy carefully for the rest of this, OH, OH. And it doesn't matter if you write HO or OH on these, you just want to make sure that the line connects to the O roughly, because that's where the carbon is actually bonded, is to the oxygen. CH2OH. If you inadvertently flip one of these hydroxyls, you could change it from a glucose to some other sugar, so you have to be really careful as you do this. Looking over here, just follow your orientations. So down, down, up. This was angled down, double check that, and then up, CH2OH. I'm usually reading in my head to check it. Down, down, up, down, that's how I'm thinking. And this is just like our other lysis into two separate molecules. So I was linked as a disaccharide and then I lysed it into two pieces. So this is my disaccharide, and then here I've lysed into two molecules. Incidentally, notice that these are exactly the same. So what I get when I break a maltose in half is two glucose molecules. So that was maltose. I'm going to leave this one for you to practice in class or ahead of time. This is lactose, and our enzyme helper would be lactase. So you want to be able to do the same thing. Look for the acetal, the hemiacetal, what's this linkage, and then hydrolyze it, break it into the two pieces.